Well, now it's time for shapes. Like
Yay.
in dancing. You have dancing waves here. So you can see the top that the E field looks like a sine wave in X.
Oh, that's what you meant.
And there is no Y dependence, so the fields along Y are going to be constant. And you can see that from the figure on the left. Sam, can you take us through that figure?
So this is the cross-section view on the XY plane. So you see E fields pointing all upwards. The density of the E field lines indicate how strong the field is at the location. So I think this kind of matches with our understanding of the E fields and H fields.
So if we have m equals 1 there in the sign description, we see that at the ends at x equals 0 and a, the field is 0. As you can see, the field strength goes to 0. That's why the curved line, which is showing what sine is. And when sine is a maximum at a over 2, then the field lines are dense.
Yeah.
The hard part are the H lines. But we do know that the H doesn't depend on the y direction for this mode. So they're constant. The values are constant. We don't know what the constants are, but those are the blue lines that cut.
And yeah, that's why the horizontal H lines are shown as like that.
Now let's look at the YZ plane. So that means we're going down the guide and we're cutting through into the page. Right, so we got y and z changing, so at fixed x. Now, we know that it's behaving like a cosine or sine, and you can see that every...
Yeah, the polarity of the E field lines would change.
Every half wavelength.
Exactly, yeah.
Yeah, and you can see that, and you can see
the
where...
change in intensity going from the beginning of the line
through the end. And so what we see, if you look at the middle, is cosine, and cosine is maximum field concentrations at the center. So there you have basically the cosine and the dashed line, and then the field lines, much like on the original diagram. And the tricky one is the XZ plane.
The top view that you can see here. Well, the diagram seems to make sense. You have H fields in a closed loop, which is physically what is required. And where there is maximum E field intensity, so where there's a lot of E field lines, there's also a lot of H field lines around here. So max E corresponding with max H, and that seems to be fine.
And the field lines close, as they should. And also the field lines change polarity at half wavelength. You can see that. See the gaps in the E, where the E changes, that's where we see the beginning on each side of the maximum, which is right there. So there's the E maximum, and you can see the density of field lines increasing here, so that corresponds. And then on each side, the
direction is different.
Yeah, the intensity changes in direction. And so that's consistent with what we know about taking paddle wheels and sticking them in electric fields and see which way the paddle twirls around. So it all makes sense. But this is for TE10. It gets a lot more complicated when you have different M's and N's. But for now, we get the idea that we can understand basically what these field lines look like. And this is a jumping off point for further analysis of shapes.
Hey, so let me take a guess. If we had, instead of TE10, we had 20. So I guess, let's say when we look at the cross-section, instead of seeing one kind of half wavelength E, we will actually see a full wavelength. Is that right?
Yes, and we did it with the slinkies.
Yeah.
When we did the waves on the standing wave on the slinky, we got the three. We got a hump up and a hump down and a hump up. And we see that in the slinky movie in our description of standing waves on the waveguide. And that would be TE30.
Oh, so like with three, oh well, I have two hands, so I can't do it.
Well, let's draw it. Maybe you can get a pen and draw what TE30 will be for the E across the cross section of the guide.
So I guess it'd be something like, well, we have three, so it has to be.
Yeah, equal in 3 pieces.
Something
Yeah,
like that.
there you go. And that's what we saw with the slinky vibrations. We had these nodes here. So it all starts to make a bit of sense. Takes a while to get the appreciation of how all the shapes interact.
Well, that's wonderful, Matt. Indeed, a very good dance
Slinky.
and wave.